How is everyone today?
All right.
Uh, Everyone staying home for Thanksgiving?
Absolutely.
How about you, Elliot?
Well, probably. I was invited to my nephew's in Maryland, but and I think it's actually could be done safely, but the New York rules are just too challenging for out-of-state travel. So.
Yeah.
We might be halfway through in time, but we're far less than halfway through in risk. Everything was
Yeah,
planned
I
this
think
spring.
that's right. Yeah, we were planning to go skiing in January and we just decided to cancel that. So,
Yeah, I was supposed to go visit my mother in Croatia, December 12th. I have a ticket. I don't think I'm going.
how are things in Croatia?
Pretty bad, horrible. They were perfect this spring and now they're horrible and they're doing nothing. They're just like, I don't understand. I mean, they clamped so hard on the spring and they had almost 0 cases, and now I think we're pretty much worse in Europe.
Well, that's a shame.
Awful. I don't really understand what the deal is. I think the deal was that they didn't want the crisis. They had an election in early July. They won an election and now they don't care. They opened, I mean, I can understand they opened everything for the spring, for the summer, because they really needed the tourist dollars and everybody opened in the summer. But I mean, that's long gone. Why they're not clamping down now, I don't understand.
Well, the U.S. isn't doing much better. So I don't understand that.
But I mean, the U.S. is crazy, but they are consistently crazy from the spring, right?
That's one way to put it.
Right? And these guys have been like totally sane in the spring and now they're crazy. Like, and it's the same guys, So like,
well, they got tired of it. I mean, they were good for a long time. Enough of that. Now we have to play. All right. So why don't we start? I want to finish the proof. Well, let me just say where we are. So we have we have W and a Morse function F. We have a critical point. A Morse singularity. And we look at the space of embeddings of the standard model, MR, R is the index of the critical point, into F, adapted to F at C0. So that means, first of all, the origin in the model goes to the critical point C0, and this function H, which is the standard function minus norm x squared plus norm y squared, where x has r coordinates, that's the r, and y has the rest. H goes to F restricted to the image. In other words, phi star of F is H. That's what it means to be an embedding adapted to F at C0. So we have that space. We have the space EL of descending elementary descending paths, starting at F and moving C0. That was the image under phi of the standard path we defined in the model, H lambda. And then we have B, which is the space of bidiscs in W coming from the space of embeddings. So any embedding of the model, well, the model has the standard x-axis, a descending manifold, and a y-axis, the ascending manifold. They go over into W to a pair of submanifolds, the descending manifold and the ascending manifold. And the union of those two is a bidisk. And it's the, so we have then a diagram. Embeddings, you can restrict the embeddings to the standard bidisk. And then you get a bidisk in M, or you can take this map that associates to an embedding the image of the standard descending disk in the model, and you end up with an elementary descending disk in W. And we proved that the fibers, well, there's a group, you can call it group of diffeomorphisms of the model, G12. These are the diffeomorphisms of the model that preserve x squared and y squared. Okay. And we proved that G12 acts simply transitively on the space of elementary, on the fibers of the mapped elementary paths. So two of these embeddings adapted to F at C naught give you the same elementary path if and only if they differ by the action of this diffeomorphism group, preserving x, norm x squared, and norm y squared. And that result comes from the formula, the explicit formula for the path H lambda, which was something like the standard H minus epsilon lambda, and then a function omega bar of x and y, some explicit function that I won't write down again. But just using the nature of that function, which involves the product with the norm of x and the norm of y and the function h, you easily deduce this result. Okay, so we have this commutative diagram. These embeddings to the paths, restriction of the embedding to the bidisk, the standard bidisk gives us bidisks. The fact that the fibers of this map are in the same orbit of this group action. This group acts simply transitively on the orbits, tells us that two embeddings with giving the same elementary path automatically give the same bidisk, because this group clearly preserves the two axes, since it preserves norm x squared and norm y squared, and therefore preserves the image of the bidisk. So you get an induced map across here, chi. And then we had to replace this space by a simplicial set, which is not the simplicial set, the usual singular simplicial set, but a subset of it. So EL tilde is a subsimplicial set of the singular simplicial set. It's the subset of all simplices in EL that can be lifted to simplices in P. So these are sigma mapping simplices into EL, for which there exists a lift. Sigma tilde mapping the simplex into P, whose image under rho is the original simplex. So as I've told you before, think about path components. You may well have 2 points in E that are connected by a path, but you can't lift that path to P. And in pi naught of the space, these 2 points would represent the same path component, obviously. But in the simplicial set where you only allow vertices, points of EL, to be connected if they're connected by an arc that comes by the image of an arc from P. So you get a different set of connected components and different higher homotopy groups. And the theorem that we're trying to prove is that this diagonal map across here, chi, from the homotopy groups of this simplicial set to the homotopy groups of, so this is based at any base point, is an isomorphism. So for example, on connected components, path connected components, this map is a bijection, and no matter what element you choose in here, you get an induced isomorphism on the higher homotopy groups. We're actually only interested in pi naught and pi 1, but the theorem is completely general. So this is a bridge between geometric information, these bidisks, which we can study in their own right, and these very special descending elementary descending paths. Okay. And the connection between these two, clearly from this diagram, comes from embeddings. So both of these objects, elementary descending paths and bidisks, are constructed out of an embedding of the standard model by 2 different operations, one pushing forward a standard elementary descending path, the other pushing forward the bidisk to get objects in W. And the statement is that those 2 are homotopy theoretically equivalent operations. Okay. So the first thing I want to do today is prove this theorem. And the proof is a statement that we have 2 fibrations that give long exact sequences of homotopy, and that those long exact sequences sort of fit together, and you do a quick diagram chase, and you have to prove one result about linear groups, basically. Sort of an obvious result to get the isomorphism. Well, actually, I shouldn't quite say that. What you do is you find something in the embedding space that's isomorphic to this group, the same thing in the embedding space is isomorphic to that group by 2 different but similar diagrams. So, and then that gives you the comparison. So let's start on this side. So we have the embeddings going down to these elementary paths. We can apply the singular simplicial functor, and by definition, the image of this is exactly the subcomplex in the elementary paths, in the singular complex of the elementary paths. So this is just the image from here. And we saw that G12, this group G12, acts, well, on points, this group acts simply transitively on the fibers. I claim the same statement is true at the level of simplicial sets. So suppose I have a simplex sigma mapping delta n into E tilde that's liftable to P. So that's an element in the n-dimensional set associated with this simplicial set. Okay, so choose a lifting, sigma tilde into P, a lift, which we know by, this is because we changed the definition from the obvious one of the simplicial set here to this more restricted subcomplex, we know there are such lifts. And now look at the fiber product of what do I want to do? Okay, so suppose I'd say it this way. Suppose I have two lifts. So the statement I'm trying to prove is if you take an element here in the n simplices of this simplicial set, and you look at the fiber over it, that is all the n simplices in this simplicial set that map to the given simplex down here, that should be a torsor of the n simplices in the group. Okay, so we want to show that there exists a unique map G of the n simplex into this group G12 such that G of T, so T is a point in the simplex, that's a multi-index. So this is a group element. That group element is then a certain diffeomorphism of P, and I want to take, say, sigma 1 tilde of T, and I should get sigma 2 tilde. In other words, sigma 1 tilde times G, thought of as a map from delta n to P, is equal sigma 2 tilde. This is provided, of course, that an obvious and necessary condition is that these have the same image when you project over into the elementary path space. But the point is that if you look at sigma 1 tilde of T and sigma 2 tilde of T, these embeddings, so these are both embeddings of the standard model into W. They have the same image. Because they cover the same elementary path, which is since they both cover sigma of T in the space of elementary paths, both map to that. And the statement that we started with is that if you have two embeddings adapted and so on that cover the same elementary path, then they differ by a group element. If they differ by a group element, they have the same image. And in fact, we let G of T simply be, I don't know, sigma 2 tilde maps over, and then sigma 1 tilde comes back. So I have two embeddings of this manifold into W with the same image. I can compose one and the inverse of the other to get a diffeomorphism of W of the model. And this is the group element that carries one to the other. So clearly sigma tilde 1 of T, G of T is sigma tilde 2 of T. So this is the element that preserves norm x squared and norm y squared. So you see now that it varies continuously with T because these guys are varying continuously with T. So this is the map G from the n simplex into G12 carrying sigma 1 tilde to sigma 2 tilde. So we, in some sense, have a fibration on the level of simplicial sets. The simplicial set of G12 acts on the simplicial set of P simply transitively, and the quotient is what I'm calling this slightly exotic simplicial set. Okay, well, now it follows from this that you have a homotopy along exact sequence, sort of elementary simplicial set theory. This is the analog of a principal fibration. So you have pi I of, well, I should put the simplicial set here, G12 at the identity into pi j, this is a j, of p at any fixed point into pi j, this should be, sorry, sigma of p. A simplicial set into the elementary paths at rho of phi. Okay, and it keeps going. So this is the homotopy along exact sequence of a fibration. Now I'll simplify things. Of course, the homotopy groups as a simplicial set are the same as the homotopy groups of the space. So I can write this slightly simply, more simply as this one, of course, I have to keep. It's not the singular simplicial set. So this isn't the same as the homotopy groups of the space EL. So that's one exact sequence. Now I have another exact sequence based on this guy. Okay. Well, first of all, P has, I want to get rid of one of the components of P. So I should have said way up at the beginning, all embeddings for P are orientation preserving. Should have said that in the beginning. So in other words, we fix once and for all an orientation of W. Our Euclidean space has an orientation. We only look at embeddings that preserve the orientation. Nevertheless, as long as R is not 0 or n, P has two components. I call them P plus and P minus, but there isn't a distinguished plus or minus. And the involution, x1 up to xr, those are the x coordinates, y1 up to yn minus r goes to minus x1, x2 up to xr, minus y1, y2 up to yn minus r, switches between these components. In other words, the component is determined by what it's doing to the orientation on each of the ascending and descending manifolds. And since the full map is to preserve the orientation, you have to, if you reverse one of the orientations, you have to reverse the other. So if R were 0 or n, then there'd only be one component. You couldn't do this operation where you switch a sign on each the x and the y. But otherwise, you can simultaneously switch the two signs. That does not affect either the elementary path, descending path you get, because those functions W were invariant under these switches, nor obviously does it change the image of the bidisk. That's the locus where y is 0 or x is 0. Okay, so I can restrict, so the image, so in other words, the image of sigma p and sigma p plus in L are the same, and likewise the image of p and p plus in B are the same. So I'm going to restrict from all of P to what I call P plus. And I have to restrict G similarly to diffeomorphisms that are orientation preserving on both of the branches, both of the ascending and descending manifolds, and this doesn't change. Okay, so that's our first sequence. Homotopy groups, it's a fibration where the fiber is this group. It's now a component of the identity of this group. P plus is one of the two components of the embedding space, and this is still the elementary paths. So the other sequence is just about, and it goes like this. So we have P plus. We can take the one jet of P plus. Let's call that J of P plus, the one jet at the origin, at the critical point. So this is just the linear transformations, linear isomorphisms at the origin, from the tangent space at the origin of the model to the tangent space at the critical point of W, and they have to send the Hessian of H at the origin to the Hessian at the critical point of F. So they have to line. So it's not an arbitrary linear transformation between these two vector spaces, linear isomorphism. It's an isomorphism that carries the standard quadratic form to the Hessian of F. And we'll talk a little bit more in a minute about what that is. And then the fiber of this map is just, we'll call PJ plus. So these are the embeddings in P plus that have the same one jet. Well, the fibers here are embeddings with a given one jet. The fiber over the point J of, so we have a particular phi in here, and J of phi would be its one jet, and then we would have the fiber would be PJ of phi. But anyway, so that's the fibration. And there's a little exercise, it's not too difficult, and I won't do it. This is a locally trivial vibration. Thus, we have a long exact sequence, the homotopy long exact sequence. Which goes pi j of pj plus at phi into pi j of p at phi into pi j of jp, this should be plus, jp plus at j of phi, the one jet of phi, and then so on. All right, now we put these two sequences together. Which way I want to do it? Let me write this sequence vertically. So pi j of pj plus phi into pi j phi plus phi into pi j of the one jets of p plus at j of phi. Sequence continues. I put the other sequence horizontally, pi j of G12 plus into pi j of this slightly exotic homotopy group associated with the descending paths. And the claim is that this diagonal composition across here, call it alpha, is an isomorphism. So alpha is simply the composition of this map and this map. Okay, so this diagram commutes. Okay, And the proof is going to be, there's another claim, this map nu is an isomorphism. So the map starting in the group, going over here and going down is an isomorphism. And then it's, so I have to prove that. And then it's an easy exercise, easy diagram chase. That alpha an isomorphism, nu an isomorphism implies alpha is an isomorphism. So if this is an isomorphism all the way up and down at every level, then this is too. And what happens is you write this group as the sum of this image and this image. Both these maps are injections. This group is a sum of the two. And therefore, yeah, so it's the sum of the two. Anything here goes non-trivially here and non-trivially over there anyway. It's an easy diagram chase. I won't do it. So what I need to prove is that nu is an isomorphism. So where does nu come from? I have G12 plus acts on P plus, and then I project to the one jet space. So there's an induced action of G12 plus on the jet space, turns out. And of course, this factors through the projection of G12 plus to its one jet space. So this again is just take the one jet at the identity, at the origin. So here you have a group of diffeomorphisms, here you have a group of linear transformations. And then that group of linear transformations, automorphisms of the origin of the tangent space at the origin, acts on the jets of the embeddings. And then G12 plus acts naturally on these embeddings. Okay, and I need to see each orbit gives a homotopy equivalence. So what I've now done is described this map. You simply let given an element in the group, you let it act on the jet of phi by taking the jet of the group, that's a linear automorphism, and letting that act on the jet of phi. So it's just this transformation. Now, what do these groups, what does the group look like, and what does the space of jets look like? Well, the jets, let's talk about the space of jets of P plus. So we have an embedding from MR into W, sending the origin to C naught, and sending the Hessian of the standard function H to the Hessian at C naught of F. So this is the standard form of type R n minus R. So if you think, what is this collection of linear transformations? Well, if you pick one, then the possible one jets here would be given by taking the given one, say one jet of phi, and acting by an arbitrary automorphism preserving the quadratic form of the domain. So then this is simply the isomorphisms, the orientation preserving isomorphisms of the quadratic form Q R n minus R, the standard quadratic form acting on J phi. So the space of one jets is isomorphic to the isometries, orientation preserving, or isometries that preserve both both the positive orientation of both the positive and the negative spaces of this quadratic form of type R n minus R. The standard form of type R n minus R, it's an orbit of that through phi. And this is usually called SO plus, let's say, R n minus R. Okay. On the other hand, the jets, the one jets of G12 plus, well, this thing preserves norm x squared and norm y squared. So it's one jet preserves both the axes. And in fact, it has to preserve the norm on both axes. So it's simply SOR cross SO n minus R. So this one is split. It preserves both the x and y axes. It preserves the norm on both those axes. So it's a product of the orthogonal, and it preserves the orientation. So it's a product of the special orthogonal groups. Whereas this guy's the isomorphisms of the quadratic form. It's a little bigger. It's this orthogonal group. You don't have to preserve the two positive and negative subspaces. Nevertheless, the inclusion of SOR cross SO n minus R into SO plus R n minus R is a homotopy equivalence. This is a subgroup and its complement is a Euclidean space. So that shows that nu is an isomorphism and hence so is alpha. So we've now shown that this map alpha from pi j of pj plus based at phi into pi j of this exotic version of the descending path space based at rho of phi. It's an isomorphism for all j. So I've compared, I want to compare, where's the theorem? The theorem says that the homotopy groups of this elementary path space are the same as the homotopy groups of the bidiscs. What I've got now is a third space, the homotopy groups of this PJ based at phi, and I've produced an isomorphism here. The next step is to produce a similar isomorphism there, and that will produce the isomorphism I'm looking for. Sorry. Now the argument, for the other isomorphism is a completely analogous argument. So we have the sequence pi j of p plus phi into pi j of bidiscs in the image of phi, beta, let's call it. And the fiber was the homotopy groups of just the fiber. Okay. Again, you have to prove that this is a long exact sequence. And that comes from the fact that this is a locally trivial fibration. Again, I'm not going to do that. It's an elementary, if somewhat intricate argument. So you have that homotopy long exact sequence. I put the same vertical sequence I had before, so let me rewrite here so I have room to put the vertical sequence. And this sequence has, again, pi j of P plus J phi, and down here, pi J of P plus J phi. And again, I'm going to show nu 1 is an isomorphism, and that will imply alpha 1 is an isomorphism by exactly the same diagram chase. So I have to compare, whereas before I was comparing G1, 2 to this space of jets, now I have to compare P, the fiber P nu to the space of jets. So once again, this map factors through the map from P plus nu to the jets, factors through the one jet of P nu plus. And this is then just, this is the inclusion of the fiber into the total space. This would take the one jet. This is simply take the one jet and then include. So we have the one jets for the fiber into the one jets for all the embeddings. And well, it's a very similar argument. This turns out to be equivalent to SO R cross SO n minus R. I mean, now we're doing linear transformation, so it's easy to see what's going on. And this is SO plus R n minus R, exactly the same groups that we saw, torsos of groups we saw before. So this is a homotopy equivalence and implies this map is an isomorphism, and therefore that one is an isomorphism. So in the end, we have compared pi j of E tilde to pi j of this jets of P plus and pi j of B. These are isomorphisms. And everything commutes, so this gives the isomorphism across here that we wanted. All right, so that's the proof of the first half of the bridge to get from bidiscs, these geometric objects, out to these elementary paths, or a slightly funny version. Now I want to go from all paths, all descending paths, and you have the inclusion of the elementary descending paths into all paths. I want to show that this is an isomorphism as well, non-homotopy groups. And that will get us that all descending paths are isomorphic to the bidiscs. Okay. So that's what I want to start on now. And I need to set up, I think all I'll be able to do the rest of the day is set up the notation and state the result on the other side. And then I'll come back after Thanksgiving and give the argument, which is in fact simpler than what we've just been through. So here's the notation that we're going to use. So we're starting over now. We will mention again elementary paths, but we're going to have others. We're going to introduce other spaces I need to talk about first. So F still our Morse function. C is still a critical point. I'm going to denote its critical value by alpha, and I'm going to suppose that's a simple critical value, meaning only one critical point. with critical value alpha naught. Okay. Well, we'll see why in a minute. And then I'm going to consider the next P critical values going down. So alpha 1, alpha P are critical values. And they are the next P as we descend. So as you just move down the real line and you say, well, alpha 1, so I started alpha naught, that's a critical value. I move down until I hit another critical value, that's alpha 1. I go to the next one, that's alpha 2, up to alpha P. Here we're fixing some integer P for the whole discussion. Okay. Okay. So the next P critical values as we descend. Okay. Now, suppose you have a path. We're going to consider paths of Morse functions. By the way, I'm not assuming that these other critical values are simple. There can be several critical points with critical value alpha 1 and so on. I make no assumptions about those. But we're going to consider paths of Morse functions that preserve the critical value order on alpha 1, alpha 2, alpha P. And so these critical values can move through the path, but they never cross each other. So alpha 1 always remains above. Well, if you have a path of Morse functions, then you can, let me back up a second. So we're going to consider a path of Morse functions. Oops. Since the Morse functions are Morse functions, so this is a path F lambda, let's call it. Lambda from 0 to 1. If you have a critical point C of C lambda of F lambda, critical, that's a Morse singularity. That implies for all lambda prime near lambda, there exists a unique critical point C lambda prime for F lambda prime in some fixed neighborhood near C lambda. Okay. So you have these isolated critical points, these Morse singularities, pick disjoint neighborhoods around them. So these are the critical points for F lambda, C lambda I for F lambda. Now as I move F lambda, these critical points move a little bit, but they stay in these disjoint neighborhoods, so they never get mixed up. So in other words, there exists, so if C naught up to CT are the critical points of F, which is F naught, then there exist paths C naught lambda up to CT lambda such that C naught lambda up to CT lambda are the critical points of F lambda. So you can follow the critical points anytime you have a path of Morse functions. You get a path of critical points. They don't mix up with each other. They don't collide. So these paths are unique. So there exist unique paths. Okay. So I started off with, suppose I had, so here are the kind of paths I'm going to consider. The critical values can move, but except for alpha naught, they do not ever meet each other. Well, maybe I should have said before that, if Ci and Cj have the same critical value, then Ci of lambda and Cj of lambda have the same critical value for all lambda in the interval. In other words, this is not very complicated. There's some number of critical points at the beginning with critical value alpha 1. Now you start moving things, alpha 1 may move, but all the critical points that started with critical value alpha 1 move with it, so that they all continue to have the same critical value, which is some path for alpha 1. Likewise for alpha 2 up to alpha p. So you're keeping the structure of how many critical points does alpha 1 have, how many critical points does alpha 2 have, and so on. In other words, no new critical values are suddenly appearing. You have these p critical values, and they, alpha 1 to alpha p, and they may move around, keeping the same number of critical points at each lambda, and they never intersect each other. Alpha naught, on the other hand, alpha naught moves.
Are you describing the surf graphic here? Really?
Well, yes, in a way. I'm just, yes, in the sense that I have these lines and they have multiplicity. So this is a more general type of graphic, a multiplicity M1, M2, and so on. And here's M naught, which goes with alpha naught. It has multiplicity 1.
Right.
And so these things can move around. Their multiplicities stay constant. So there's not suddenly of these M1 critical points, one pops out. They all move together as far as their critical value is concerned.
Right.
They can go up and down. They never cross each other, except this one. And this one crosses all the others. So those are the kind of paths I'm considering. It's a one parameter family. They're not generic because generically all the critical values are simple, have multiplicity 1. Those are the kind of paths we're eventually going to deal with. But for some reason here, and reasons I won't go into, you want to allow a slightly more general picture of these graphics with multiplicity, but you require the multiplicities are constant. These multiplicities don't ever split. Right? Yeah, so I have these graphs, the multiplicities. This is a single multiplicity 1, and it crosses all the others. Yeah, thank you for asking that question. And it crosses down, and it doesn't cross back. It crosses each one of the others once. So that's the set of paths. And I'll call that set, and these crossings really go from one side to another. These are crossings. Okay, I'll talk about that and just formulate that in just a second. But let me introduce a little notation. So let's let C, P, F be these crossing functions. So there's lots of extra information that I haven't written down here. The multiplicities of these other critical values stays the same. They don't cross each other, but alpha naught crosses the P of them. So P is how many alpha naught crosses. Everything else is implicit in the notation. F is the starting point. So beginning at F. So these are families of Morse functions but not generic unless all these other multiplicities are 1. Okay, so now let F P, so that's a space of paths. So this is a space of paths in F. FPF is a subspace of F. It's the subspace that contains all these paths. So it's the union over gamma in this space of paths and T in the interval of gamma of T. So it's all points that that these paths can pass through. And this is a union of strata. The generic stratum is Morse, but with given multiplicities for critical values. And the codimension 1 is when F of C naught, F lambda of C naught equals alpha J of lambda for some J greater than 0. The collision points, these crossing points. So FPF naught is the generic open stratum, the codimension 0 open stratum. And F1P is codimension 1 when there is a crossing. Maybe I should just say I've generalized the notation or generalized what we're talking about a little bit from what I talked about earlier when I had the codimension 0 strata were the generic Morse functions with no, where every critical value was simple. Here, I'm talking about a subspace which is not in the codimension 0 locus. It's in a higher codimension locus inside F, but I'm just concentrating attention on this subspace. And in its own right, the subspace gets a stratification in which the open dense set are not open dense in all of F because this isn't an open subset. It's these Morse functions with exactly the multiplicities prescribed by F. And then the codimension 1 stratum when you have that one extra multiplicity when alpha naught agrees with one of the alpha J. But nevertheless, it is in its own right, codimension 1 stratified. It's somehow transverse to the lower stratification of F, and the codimension 1 strata are the intersections with the one higher codimension strata in F. Anyway, it's sort of an obvious extension. And now we're looking at paths gamma with gamma of 0 and gamma of 1, these generic things, so not crossing points, and there exists T1 less than T2 less than TP, where gamma of T crosses the codimension 1 stratum. And this thing is codimension 1 in the strong, smooth sense. It's given by a smooth function. It's the zeros of a smooth function. So locally, this thing is a manifold, and this is F1, FP, and this is F naught, FP. These are infinite dimensional manifolds, and the path is required to go locally from one side to the other. So it crosses, gamma crosses, locally crosses F1, FP at certain parameter values. Okay. So that's our space of paths. And this is a sub-stratified space inside F where they live. And now we want to extend this notion of, well, so let me say each path in CPF is what I'll call a good path with respect to the stratification of FPF1. Okay. In the sense that I was just stating.
Can I ask, I mean, are we fixing the I mean, there is no implicit fixing of the multiplicities here, or is there?
No, there is. So
There is.
F has
Depending on the original F, there is
yeah,
a
F has a certain multiplicity, which I'm not
So this is all
specifying. And then
the-
all of them have that same multiplicity,
Yeah.
except in these crossing points.
Right.
Okay. What I want to say. So by a good path, I mean exactly what I was describing. It starts and ends at the generic situation where the singleton is different from all the other multiplicities. It has P parameter values where it crosses in sequence each one of the codimension 1 strata. It comes in agreement with alpha 1, alpha 2, and so on. And when it comes into agreement, it crosses. So that's what I mean by a good, from one side to the other locally. That's what I mean by a good path.
But they all start at F.
They all start at F.
Yeah, okay.
Now I'm going to consider the space where I don't specify where they start, but they have to be homotopic to F. So this is a space of good paths with P crossings that are homotopic in the space of good paths to a path in CPF. Okay. So these are paths that cross, say P was 2, so and here's F. It could be any path that starts at some F prime and crosses, this is where it crosses alpha 1, and this is where it crosses alpha 2. And here's its critical point, alpha 0.
Okay, so.
But you have to
CPF
have a path starting at F and a homotopy between them. So in particular,
CPF were all the paths that were on some path that started at F.
say again?
The CPF were all paths that were on some path that started at F?
No, CPF is a space of paths.
Right.
It's a space of all good paths starting at F. So we're fixing the initial point.
Right.
Okay. Now I want to look at a more general class of good paths. So good still means they start and end in the generic region and they cross in sequence these other critical values, alpha 1 up to alpha P, and these move in the same way. They move without changing the multiplicity of the alpha. So exactly the same definition of what a good path is. It's just not required to start at F. but I only want to consider the paths that are homotopic through good paths to F. So there has to be a map of the disk of the two disk of the square into this space, and on one edge it's a path, generic path between F and F prime. At the other edge, it's a generic path connecting F1 to F prime 1. And in the middle, when I go in the other direction, for each T, it's a good path. So it's a good path. Its initial point and its final point are not allowed to cross this codimension 1 stratum. And I have a homotopy of these good paths. Okay. You want to ask another question?
So basically, if I go from F to F prime and then down, I have a path in CFP.
That's right. This would be a path in CPF, exactly.
Okay.
And you could even go here to here to here, and you'd have another path in CPF with the same starting and ending point as F. And it would be homotopic rel those endpoints to F through good paths.
Okay.
Okay. So the point here is that now, what I want to say. Okay, and then we have the elementary paths of this nature. So these are elementary descending paths. Starting at some point homotopic to F that cross P critical values. So just the good paths that happen to be elementary paths. And so that's a subspace of CP. Likewise, we have the elementary paths starting in F, subspace of CPF. Okay. All right. Now I think I'm in position to state, well, almost to state the theorem. So I need another group acting. I'm going to call it GE. It's the component of the identity of the diffeomorphisms, orientation preserving diffeomorphisms of W across the diffeomorphisms of the interval. Okay, so this is the group that naturally acts on the space of Morse functions, preserving all the stratification and so on. And now I'm going to define a singular subcomplex, very similar to what I did before, inside the singular complex of these elementary paths with P crossings. So this time I don't have a space of, I need some geometry, and I want to take the image from the geometry of the simplices rather than taking all simplices. This time, the geometry I have is not the space of embeddings, it's this space of diffeomorphisms, GE. So I say a simplex, the singular simplex for this space of elementary paths is in this subcomplex, EL tilde P, means there exists a gamma in EL of P and a simplex tau in the group such that sigma is gamma acted on by, I guess on the other side, acted on by tau. So in other words, there's an orbit of the group action, the orbit through gamma, and a simplex in that orbit that lifts the simplex, from the path space up into the group. So it gives me some sort of geometric control on these paths, and it gives a different complex, a different pi naught than if you just were to use the naive pi naught. Okay, and now there's a little exercise. Again, I won't go through it. I can do the same thing for the paths that begin at F. For this, we get the same definition as the one coming from embeddings. So I could look at embeddings and take a simplicial set that they define in here, or I could look at this group and take the simplicial set that it defines. Turns out you get exactly the same notion, not surprisingly, but I won't go through that exercise. All right, so now I can state the theorem that we'll start working on next time, which is the other half of the bridge. So F is a Morse function. C is a critical point. Alpha naught equals F of C naught is simple critical value. So multiplicity 1. Alpha naught less than alpha 1 less than alpha p are the next p critical values. They're allowed to have multiplicity. We then have what we've just been talking about, this space of paths starting at F, the cross elementary paths starting at F that cross these P critical levels inside all the paths starting at F. This induces an isomorphism on path components. And for each beta in the domain, the inclusion induces pi j to pi j cp F is an isomorphism. So I could have said pi for all j greater than or equal to 1. I could have said for all j greater than or equal to 0. So the elementary paths are isomorphic with this slightly strange simplicial topology, are homotopy equivalent to the space of all paths beginning at F. So all paths that make P crossings and the elementary paths making P crossings, both starting from F, are homotopy equivalent spaces. And then we get as a corollary, what we're really interested in is that if you look at the space of paths starting in F making P crossings, it's homotopy equivalent to the space of bidiscs at the image point. So the space of paths, space of descending paths is equivalent, homotopy equivalent, to the space of descending disks. So this says, suppose you have one of these paths. So here's a path, F lambda, starting at F and making P crossings, alpha 1, alpha P. Okay, there's that path. Then in the manifold, So we have this critical point C naught. In the manifold, we can find a descending disk coming out of C naught. I won't worry about the ascending disk that crosses these P levels, alpha 1, alpha 2, alpha P, so that the elementary path associated with is homotopic in the space of good paths to this path. So up to deforming this path by homotopy of good paths, you can assume it comes from an embedding of a descending disk, and therefore then the Morse model and the associated standard path. So every path like this is homotopic to one of those, and in the space of all of them, the homotopy groups are the same. So these paths, these are paths in this two-dimensional, in some sense, in the two-dimensional, the only thing I'm recording about these paths is the critical value at C naught, and I'm watching it cross the other critical values. Here I'm talking about geometric information in the manifold W cross V cross I, so in the manifold W. And the statement is that all of these paths up to homotopy come from this nice geometric information. And this is the sort of thing that we will be able to study. We can understand what these descending disks look like in various contexts, and that's what we'll do once we prove this theorem, to start making moves. So in other words, to make a move by some elementary path, you just need to find an embedded disk, a descending disk. So this is how we're going to control what moves we can make. The moves that we can make, at least as far as these crossings are concerned, all come from embeddings of descending disks. And so if you want to know if a path is possible, you just have to ask, is it possible to move critical point C naught past critical point C1 by one of these paths? You're going to make one crossing of C1. Is that possible or not? It may be, it may not. Depends on information about C naught and C1. Well, the answer is, can you find a descending disk for C naught that passes the critical level for C1? If you can, then there is a path. Conversely, if there is a path, you can find such a disk. So that's how we're going to use this result. So what I'll do after Thanksgiving is I will go through the proof of this theorem. The proof is by induction on P. You do it for P equal 1. It's a special argument, and then you just chop things up in a fairly obvious way and do the inductive step. So it's not such a difficult argument in the end. And then we'll start using it to simplify our graphs. So this has turned the question of, at least for crossings, simplifying graphs into finding these embedded descending manifolds with whatever property you need. All right. Well, have a good Thanksgiving. Stay safe. If you go visit people, I hope you come back safe and they come back safe.
You too.
And for you, those of you still hanging in there, I'll see you after Thanksgiving. All right.
Thank you. Happy Thanksgiving.
Yeah, you too. So long.